A spacecraft pointed its ultraviolet spectrometer toward a faint blur moving through deep space. At first, the signal looked ordinary, just another trace of water vapor drifting from a comet's sun-warmed surface. But the numbers didn't match. The hydrogen emission was too strong. The mass loss rate was impossibly high, and the chemical fingerprints didn't behave like anything astronomers had predicted. Imagine being the first scientist to see that data curve rise higher than it should. Your screen shows a hydrogen cloud extending millions of kilometers into space, far larger than the brightness of the nucleus could explain, far more intense than any model predicted. What would you do if you were the first person to see this? The object is called 3I Atlas, and for the first time since its discovery, we may finally understand what it's truly made of. Not guesses, not speculation, real chemistry, real structure, real clues about a world forged around another star. And some of these clues point to a composition that has never been observed in any typical comet from our own solar system. 3I Atlas began as a faint, distant visitor crossing the outer regions of our solar system. It brightened slowly, losing mass as sunlight warmed its surface. Dust lifted, ice sublimated, gas expanded outward into the vacuum. Everything looked normal until it didn't. When ultraviolet sensors detected an unexpectedly massive hydrogen cloud stretching across space, astronomers stopped everything. Hydrogen clouds form around every active comet as solar radiation splits water molecules into their components. But the hydrogen envelope around this one was too large for the brightness we observed, too extended for the predicted size of the nucleus, too intense for the rate of sublimation expected at that distance from our star. Something fundamental wasn't adding up. Comment what you think is happening, even one word. This wasn't the only anomaly. 3I Atlas brightened faster than computational models predicted. It survived its close solar approach more intact than expected, and its coma showed signs of asymmetry that hinted at complex chemistry beneath the surface. Asymmetry means uneven outgassing. Uneven outgassing means structural variation. Structural variation means layers. Layers mean history. Inside the data, something was speaking. Something from another star system. Something our instruments were only beginning to translate. But there was another detail that made scientists pause. The object's trajectory showed it had been traveling through interstellar space for an incomprehensible amount of time. Cosmic rays had bombarded its surface for millions of years, maybe billions. Each impact altered molecules. Each collision rewrote chemistry. This wasn't just a comet. It was a time capsule from a stellar environment we would never witness firsthand. And it was currently passing through our neighborhood, shedding pieces of itself into space. To understand the true nature of 3I Atlas, scientists focused on three distinct signatures: the hydrogen cloud, the mass loss, and the spectral fingerprints. Each one reveals a different chapter of the story. The hydrogen cloud surrounding 3I Atlas is immense, so large that some spacecraft detected it even when the nucleus was too faint to resolve directly. This cloud forms when water molecules break apart under solar radiation, releasing hydrogen that drifts away at high speeds. But the scale of this hydrogen envelope implies something crucial. 3I Atlas contains far more volatile ice than expected. Water alone cannot explain the strength of the signal. There had to be additional contributors, molecules that break apart even more efficiently, producing hydrogen at rates unmatched by typical comets. Candidates include methanol, hydrocarbons, ammonia, and complex organics, all substances found in some solar system comets, but rarely at such concentrations. The hydrogen production rate suggests that somewhere deep inside this object, pockets of highly volatile material are being exposed to sunlight for the first time in eons. Fresh ice. Pristine chemistry, untouched by thermal processing. This is what makes interstellar objects so valuable. They carry material that has never been altered by proximity to our star. Preliminary estimates suggest 3I Atlas may have already lost around 13% of its total mass during its solar encounter. This is enormous. Such a high mass loss fraction suggests several possibilities. The nucleus may be smaller than originally thought. The surface layers were unusually fragile. Sublimation exposed deeper, pristine material buried beneath. Or exotic ices may dominate parts of the interior. Mass loss is the comet's voice. It tells us what it's made of. And 3I Atlas is speaking loudly. But there's a contradiction hidden in this data. If the nucleus is small, the hydrogen cloud should be smaller. If the nucleus is large, the mass loss fraction should be lower. Both cannot be true simultaneously, unless the internal structure is far more complex than we assumed. Unless pockets of trapped volatiles are releasing suddenly, not gradually. Unless the surface is fracturing in ways we haven't observed before. Spectroscopic analysis reveals something even more intriguing. Certain wavelengths indicate an excess of carbon dioxide, carbon monoxide, and potentially metal-rich grains embedded in the dust stream. Carbon dioxide is common in comets, but the ratios measured so far push the limits of what solar system models consider typical. Carbon monoxide is even more unusual. It requires extremely cold formation conditions, temperatures far below what we see in the region where most comets from our system originally formed. This means one thing. 3I Atlas likely formed in a colder, more extreme region around its parent star. Farther out than our Kuiper belt, colder than our Oort cloud, possibly near the outer reaches of a distant protoplanetary disk where temperatures approached interstellar conditions. A equals natural comet chemistry. B equals something unusual. C equals entirely new physics. Comment A, B, or C. But there is another clue hidden in the data. When you compare 3I Atlas to solar system comets, the ratios of certain molecules point to a place with far less radiation, far deeper cold, and far slower early-stage evolution. This comet may be carrying the chemical memory of its birth system, a snapshot of conditions no longer found anywhere near our star. The metals are particularly puzzling. Spectroscopic signatures suggest iron-rich silicate grains mixed within the dust. Not pure metal, but metal-enriched fragments that imply rapid formation in a dense region, then ejection into deep space through gravitational disturbance, possibly a planetary migration event, possibly a close stellar encounter, possibly the death throes of the parent system itself. We don't know, but the chemistry is speaking. Despite the new data, several mysteries remain unsolved, and some of them challenge our fundamental understanding of comet behavior. The hydrogen cloud is too large for the measured brightness, unless a significant portion of the outgassing is coming from deep interior pockets exposed suddenly, not gradually. Why would the surface rupture like that? What internal structure would allow trapped ice to release so explosively? One possibility is thermal stress. As the object approached our star, the surface heated unevenly. Subsurface ice expanded faster than the surface could accommodate. Cracks formed, pockets ruptured, volatiles escaped in bursts. But this doesn't fully explain the hydrogen cloud's size. Even with explosive outgassing, the total volume of gas released would need to be far greater than what the brightness suggests. Unless the nucleus is porous, unless the interior is riddled with voids and channels, unless the structure is more like a sponge than a solid chunk of ice. The abundance of carbon monoxide challenges our understanding of formation temperatures. No solar system comet has ever shown this exact ratio at this stage of its orbit. It suggests formation in a region colder than anything we've directly observed in our own system. Carbon monoxide sublimation temperature is extremely low. It should have evaporated long ago if the object had ever experienced warmth during its formation, but it didn't, which means 3I Atlas formed far from its parent star and remained cold for its entire existence until now. This is the first time this material has experienced significant heat. The first time these molecules have felt stellar radiation strong enough to break them apart. We are witnessing the awakening of chemistry that has been frozen for billions of years. Some instruments detected signs of metallic grains mixed within the dust. Not pure metal, but metal-rich silicate fragments that imply fast formation in a dense region, then ejection into deep space through gravitational disturbance. This creates a problem. Metal-rich grains form close to stars, where temperatures are high, where rock and metal condense first, but carbon monoxide-rich ice forms far from stars, where temperatures are low, where volatiles can survive. How does one object contain both? The answer may lie in the chaotic early stages of planetary system formation. When planets migrate, when gravitational interactions scatter material across vast distances, when debris from the inner regions mixes with ice from the outer regions, 3I Atlas may be a hybrid. A core forged in deep cold, a mantle of organics deposited over time, and dust grains loaded with metallic traces from a dense inner region, all mixed together, all ejected together, all traveling together through interstellar space. Does this change how you see humanity's place in the universe? Because this comet is not just an object. It is a geological and chemical history book, torn from another star's past, delivered to our doorstep. Slow the camera down. Imagine floating beside this visitor, seeing its jets spray crystals into space, each grain a fragment of a world that once orbited another star. 3I Atlas is older than Earth, older than our planets, older than every ocean and every mountain. It traveled through interstellar darkness for millions of years, maybe billions. During that time, cosmic rays carved through its surface, altering molecules, rewriting chemistry. Every atom inside this object carries the memory of a place we will never see, a star we cannot name, a planetary system that may no longer exist. And now, for a brief moment, it is here, close enough to study, close enough to measure, close enough to reveal secrets no spacecraft has ever touched before. Write one sentence. This means, because it truly does mean something, it means planetary systems eject material far more often than we once believed. It means star formation is messy, violent, and filled with debris that drifts between worlds. It means the chemistry of distant systems is not only detectable, it is physically arriving at our doorstep. 3I Atlas is evidence that the galaxy is not distant. It is connected, interwoven, alive. Every star sheds material. Every planetary system scatters debris. And that debris crosses the void, traveling for eons, carrying information, carrying chemistry, carrying stories. We used to think the space between stars was empty. We were wrong. The galaxy is filled with wanderers, objects like 3i Atlas, carrying messages from distant stellar environments. And occasionally, one of them passes close enough for us to read. This object is a messenger, but it is also a mirror. It reminds us that our own solar system does the same thing. Our comets are being ejected. Our asteroids are being scattered. Our material is drifting into interstellar space. Billions of years from now, some distant civilization may detect a fragment of Earth, analyze its chemistry, wonder about the star it came from, the same way we wonder about 3i Atlas. In the coming months, telescopes will continue to analyze the chemistry of 3i Atlas. Ultraviolet spectrometers will track hydrogen loss as the object moves away. Infrared instruments will map carbon dioxide and carbon monoxide release. Photometry will measure fading brightness. Orbital calculations will refine its exact path through space. We will gather more data, but we will never fully understand this object. Not completely, not entirely, because 3i Atlas will leave our solar system soon. It will fade. Its hydrogen cloud will dissipate. Its dust will scatter. Its tail will thin into the darkness. And the object will return to the silence of interstellar space, carrying the chemical story of a forgotten star system across the galaxy. We will watch it go. And we will know that somewhere out there, another fragment is already on its way toward us. Another visitor, another messenger, another piece of the galaxy's hidden architecture. 3i Atlas is not only a traveler, it is a reminder. The unknown is not empty, it is asking us to look closer.